So, we could not finish the covalent solids in the last lecture. So, we will do the remaining part here, and then we will continue with the ionic solids, the introduction to ionic solids. So, we were talking about the formation of covalent solids. We talked about why hybridization is important, just beyond the orbital overlap, because orbital overlap is not sufficient to explain why certain kind of bonding why covalent bonding occurs with 4 neighbors in solids like methane and silicon and carbon, and that is where the concept of hybridization came. So, we are looking at the structure of graphite. Graphite is sp2 bonded material in which carbon atoms are sp2 hybridized and bonded in the plane. So, it makes a hexagonal sheet, but the sheets are themselves bonded to each other with van der Waals or secondary bonding, and that is why the interaction between the sheets is weaker. And so, when you apply force to graphite, the sheets get sheared very easily. As a result, graphite is used as a lubricant. Second form of carbon that we are going to talk about is diamond, which is again a form of carbon. So, in this case, carbon atoms are sp3 hybridized and very strong directional, because the angle has to be maintained. The covalent bond can only form at certain angle and certain direction. That is why there is very strong directionality with the covalent bond. So, this I forgot to mention in my earlier lecture, that covalent bonds, because of this necessity for the orbitals to align and overlap along certain axes, there is a very strong directionality with the covalent bond. So, for example, in case of diamond, what happens is that if you make a unit cell of diamond, so in this case carbon atoms are arranged on the face centers of a cube, and then carbon atoms are arranged in such a fashion, so they are also present at the tetrahedral sites, but not all tetrahedral sites are present, otherwise you will violate the covalent bonding. So, carbon atoms are present in such a fashion, you have a carbon atom here which is covalently bonded with respect to this, that and the one here and the one here. Okay. So, they will make a tetrahedra. So, it will make a bond here. Sorry, this is, let me just draw it again. So, it will make 4 bonds. So, this is first neighbor, this is second neighbor, this is third neighbor, and this is fourth neighbor. Similarly, you will have one atom here just across the face diagonal. Other 2 carbon atoms do not go in the bottom side, they go here. So, one carbon atom goes here and one carbon atom goes here. If you put carbon atom on all the tetrahedral sites, then some carbon atoms will end up having 8 neighbors, and that is not permitted by sp3 hybridization and bonding. So, as a result, you have to arrange the carbon atoms in such a fashion so that you have a tetrahedrally coordinated structure. So, let me just show you one view graph of this structure, how it looks like. So, this is the view graph of diamond cubic structure, in which carbon atoms are of course sp3 hybridized. So, this is the unit cell, the one you see. So, this the one in the blue is the unit cell. So, there are 4 atoms. So, these grey ones are the 4 atoms, the dark grey ones, and the light grey ones are same atoms, they are carbon atoms, but they are just colored slightly differently. You can see that this is first tetrahedra, this is second tetrahedra, and the other tetrahedra is this and that. So, the other tetrahedra on the bottom side is not directly below the tetrahedra which is on the top. So, there is an alternating kind of arrangement of carbon atoms. So, you can see that in this, the one on the right, this is the first carbon atom, this is the second carbon atom, and this is the third carbon atom, this is the fourth carbon atom. You can see that each of them is tetrahedrally coordinated, and same is true about the carbon atoms sitting at the corners and face centers. They are also tetrahedrally coordinated, because if you keep the unit cell corner from dark gray to light gray, then what you will see is that the light gray will make a FCC unit cell and the dark gray will occupy the tetrahedral voids. So basically diamond cubic structure is two interpenetrating FCC lattices shifted to each other with respect to by a vector 1 by 4, 1 by 4, 1 by 4. So this is the structure you can see, this is the top view. So this, so the one, so this is the this, these make the original lattice, okay, FCC lattice. These are the tetrahedral ones, 1 by 4, 3 by 4, 3 by 4, 1 by 4, x, y you can see is obvious. So this is, if this is x, this is y, what you see is only the z. Now you can make the unit cell by placing the, by shifting the unit cell little bit. I can make the unit cell here. If I can take, if I make a unit cell like this, I can make a variable unit cell which is this. If I do that, I have an atom here which is equivalent to this atom at 3 by 4, 3 by 4. I will have an atom here which is equivalent to this atom 3 by 4, again at 3 by 4, and again I will have this atom. Now if you make 3 by 4 as 0, the 1 by 4 will become half, alright. So you will make a FCC lattice of these, and tetrahedral atoms will become, this will become a tetrahedral atom, this will become a tetrahedral atom, this will become a tetrahedral atom, and this will become a tetrahedral atom. So basically these are two interpenetrating FCC lattices into each other shifted by a vector quarter, 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 okay, and this lattice is called as diamond cubic lattice. And this is followed by diamond, it is followed by silicon, but it is also followed by silicon carbide and cubic zinc sulfide, okay. So what happens in silicon carbide is that in silicon carbide this atom will be silicon and this atom will be carbon, or you can say this is carbon, this is silicon, both are possible, right. You just have to shift the lattice corner. Similarly in case of zinc oxide, this would be zinc, this would be, or sulfide, this would be sulfur. You can make this as zinc, this as sulfur, both are possible representations, okay. But zinc sulfide has slightly ionic character, so that is why we will discuss the structure of zinc sulfide in case of ionic solids. But diamond, silicon carbide, or even silicon has this kind of structure which is called as diamond cubic lattice. But diamond cubic lattice is not a Bravais lattice, okay. Remember, it is not a Bravais lattice, it is still a face centered cubic lattice. It is still a face centered cubic lattice, but the motif is different. Motif is face centered cubic lattice 0, 0, 0 and 1 by 4, 1 by 4, 1 by 4. That will be the motif, because you have two atoms. So it's a lattice which contains 8 atoms, okay. You can calculate the packing fraction. You can see that diamond atom is sitting, carbon atom is sitting as a tetrahedral site. Tetrahedral site size is 0.225 R, and you have the same size atom sitting there, which means the lattice has to dilate. So lattice of silicon or carbon is bigger than what it would have been if there was no tetrahedral atom, okay. Of course that is not possible bonding wise, but imagine if carbon only made FCC lattice, then the packing fraction would be same as 0.74, but in this case packing fraction would be lower because you have to dilate the lattice. So you can calculate the packing fraction by yourself. Alright, this is the structure of diamond. This is the structure of another covalent material called as C60, which is the fullerene buckyball kind of structure. So it has a football shaped structure where carbon atoms are arranged in such a fashion so that you see these truncated, you see these hexagons and pentagons arranged. So you can see that if you only had pentagons, it will not make a structure, but if you put pentagons separated by hexagons, then it can make a ball kind of structure. So this is C60 molecule which is called as fullerene, and this is the structure of, this is again a covalently bonded materials. You can see that each atom having three neighbors here, sp2 hybridized structure. And then there are some other covalent solids, these are the ones which I discussed in the beginning. So, for example, iodine makes a structure like this. So, iodine is a orthorhombic structured material, it has linear one fold coordination. So, these are iodine atoms, this is one I, this is second I. So, it has only one neighbor. So, dumbbell shaped molecules arranged in an orthorhombic lattice. This is structure of tellurium, which is a spiral structure, it is a hexagonal, it again has twofold coordination in a spiral network. So, these are the basically covalently bonded structured materials which we wanted to discuss in this lecture. So, what we will do now is we will move on to we will continue what we were doing. Okay, so I will just write here. So, we have other examples are silicon carbide, zinc sulfide, similar structures. So, you can say structure is diamond cubic lattice, not a Bravais lattice, very important to remember, not a separate Bravais lattice. So, basically Bravais lattice is FCC with motif at 0 0 0 and 1 by 4 1 by 4 1 by 4. Okay. So, basically it is a mixture of two interpenetrating FCC lattices. In case of silicon carbide and zinc sulfide, there will be two FCC lattices, one of silicon and one of carbon. Similarly, in zinc sulfide it will be one of zinc and one of sulfur. So, now we will start the discussion on ionic solids, and this discussion is important because many compounds that we see around us, they are all ionically bonded materials. And for example, if you see compounds like sodium chloride, potassium chloride, several oxides, nickel oxide, copper oxide, iron oxide, compounds such as barium titanate and alumina, even zinc oxide, several materials, they are all ionically bonded materials, and they may not be 100% ionic, because that is determined by, because ionic bond forms when there is a large difference between the electronegativity of two atoms. So, for example, in case of sodium you have lithium fluoride, another example. So, when the elements have large difference in the electronegativity, bond is predominantly ionic. In some cases, when the difference is not large, the bond may be partly covalent. In most cases it is partly covalent and partly ionic, but they fall in the category of predominantly with ionic character. So, bonding in this case is predominantly ionic. Exceptions may have covalent character. So, for example, zinc oxide, zinc sulfide, silicon carbide and all that. So, percentage ionicity or ionic bond is proportional to difference in the electronegativity of let us say A and X, where A is cation, X is anion. So, if you look at, for example, the periodic table, on the left we have let us say 1A, then we have 2A, and in 1A we start with hydrogen, lithium, then we have sodium, then we have potassium, and so on and so forth. Lithium has an electronegativity of 1.0, sodium has a electronegativity of 0.9, potassium has a negativity of 0.8. In the second one we start with beryllium, then we have magnesium, then we have calcium. Magnesium has an electronegativity of 1.2, calcium has a electronegativity of nearly 1. Then of course you go to group 3, these transition elements in between, and then we, how many of them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we go to group 3B, and then we have 3A, I think this is 4A, and then we have 5, then we have 6, and then we have 7, and of course then we have inert gases. So on this side we have in group 4 we have atoms like carbon, silicon, and there are bismuth and all that. So carbon has electronegativity of 2.5, silicon has electronegativity of 1.8, and then important one is again group 6, where you have oxygen, which has a electronegativity of 3.5, and then you have sulfur, which has a electronegativity of 2.5, and then we have fluorine, which has a electronegativity of 4, chlorine has a negativity of 3, and so on and so forth. I am not writing for all of them, but when you mix these compounds, for example lithium and fluorine, it is a large difference in the electronegativity. If you mix chlorine and sodium, it is a large difference between the electronegativity. If you mix, for example, potassium with chlorine, you can have large difference in the electronegativity. You can mix magnesium with oxygen, calcium with oxygen. These all have fairly large difference in the electronegativity, and these all give you large ionicity in the bonding. So for example, anything like calcium fluoride, lithium fluoride will give you a largely ionic bond. But on the other hand, if you look at silicon carbide, silicon carbon, the difference is hardly any difference, 1.8, 2.5. So this is predominantly covalent. Similarly, if you look at zinc sulfide, zinc is just before column 3, so this is zinc. Zinc has a electronegativity of 1.8. If you look at zinc oxide is more ionic, but zinc sulfide is less ionic. Zinc sulfide is more covalent in nature. So this is the reason why you have this variety of compound showing predominantly ionic behavior, compound showing predominantly covalent behavior, and compound showing mixed behavior. Okay, but all of them they have certain ionic character, that is why they fall in the category of ionic solids. So first, before we go into how ionic solids form, let us first look into what makes ionic structures stable. So why is that when you put several anions and cations together, they form these structures which are periodic in nature. They have certain crystal structures with regular periodicity rather than making isolated molecules. Why can't you just have one silicon carbide or maybe one zinc oxide molecule, another zinc oxide molecule? Then why do they have to arrange themselves in a periodic fashion? Why can't just you have zinc oxide molecule? That is it. So you can have several zinc oxide molecules which are randomly located in the space. Now this is to do with the energetics. So here if you look at basically the cations are defined by their the energy that we consider in case of cations is ionization energy, right. the energy required to ionize them. In case of anions, what we consider is electron affinity, because they are ready to accept the electron. That is why we talk about electron affinity. The energy of an ionic bond is determined by when you put these atoms together, you have Coulombic attraction and you have repulsion. Okay, repulsion is often called as polyrepulsion. Okay, so when you put A and X, this is A plus, X minus, there is a tendency to attract. But suppose you have a AX molecule. Okay, you have another AX molecule in the vicinity. Suppose if it was in this position, it will have tendency to attract. Suppose you have AX and the neighboring molecule says it was oriented in such a fashion so that there is a X coming closer. This will have tendency to repel. So, the balance of these attractive and repulsive forces eventually leads to a structure which is periodic in nature. That is why the molecules are not randomly just arranged, because if molecules are randomly arranged, you will have AA close to each other. In some cases you will have AX close in. So you have to have a balance of forces. So basically the energy expression of this structure is something like that. You have n number of atoms. This is epsilon j minus of qi qj divided by 4 pi epsilon naught r ij. So I is the reference atom or reference ion, and then you have these two terms, one is the attraction term, second is the repulsion term, Bij divided by Rij to the power n, and B is a constant here and n takes a value of about 10 in this case. So for every jth neighbor, you got to sum this energy and multiply by n, which is the number of molecules in the system. So this will eventually give you an energy landscape which will, so basically you have two terms here. First term goes as minus of 1 over r, and the second term goes as r to the power n. Okay, it is the combination. So this is a force which is attractive in nature, and this is a force which is repulsive in nature. It is the balance of these two forces which will determine whether you will have a minima in energy for a structure when you arrange the atoms in a periodic fashion. So there are multiple possibilities. You try and minimize the energy for those possibilities and see for which possibility the energy is minimum. So basically when you bring, for example, sodium and chlorine together, let us say you have sodium plus and you have chlorine. When you bring them together, you form NaCl bond. It's not exact relation, but sort of NaCl bond. So this is basically when you bring them together, you spend energy. So you spend energy to bring them together. And what is that energy? Which is, so I wrote earlier, ionization energy, let us say I write it as E1, EI, and electron affinity I can write it as chi A. Okay. So it is the difference between EI and chi A. This is the amount of energy I need to spend in creating a bond. And then Second is the energy gained. Energy gained is called as cohesive energy, which is achieved by bringing the atoms together. So, what you do is that you make a periodic structure in that case. So, you will have for example, this is sodium atom, this is chlorine, this is chlorine, this is chlorine, and so on and so forth. You will have this ensemble of ions in this fashion. So, basically you arrange them in a periodic fashion. It is not exact representation, but I understand, I hope you understand what I mean. So, this is not a right way to do it. Let me just show you. So, the bottom one plane would be something like that. This is chlorine atom, these will be sodium atoms. So, these are all sodium, these are all chlorine, this is sodium. So, you put them together, when you bring them together you gain energy in the form of cohesive energy, and you need to then worry about whether there is a net attraction or not. If there is a net attraction, then the structure is stable. If there is no attraction, if there is more repulsion, the structure is not stable. So, the overall curve, the energy landscape would look like that. So, if you draw this is potential energy, and this is typically in kilojoules per mole, and this is the distance r. So, your repulsion term goes rather rapidly, something like that, very rapidly. This is the repulsion, and then you have the total energy, and your attraction term goes very close to what this is basically. So, this would be the term which is attraction, and this is what is going to give you the minima. So, this is the potential energy minima, this is the equilibrium separation R naught, this is nearly 236 picometer approximately. You can see that higher distances give you higher energy. So, at this distance you have lower energy. So, this is in R in picometer, and at very low values you have very high repulsion. So, if you go lower than 236 your repulsion increases, and if you go higher than 236 then again although it is attractive, the energy is not minimum, the energy tends to increase. So, this is the point at which you hang around to between silicon and. So, if you talk about very large small distances, it is like this, silicon and chlorine, sodium and chlorine is squashed together really very close. So, that means high repulsion, this will mean high repulsion, and if you come somewhere here then it would mean situation like this, sorry, NaCl. So, they will tend to attract, but then they are too far off. Okay. So, they become like isolated atoms. So, chlorine is somewhere there, sodium is there is attraction, but that is a weak attraction, and then you are somewhere here. So, that is where you are sodium and chlorine, they are happily without squashing each other, happy with each other. So, this is the energetics of ionic solids, and we will look at the details of this energetics a little bit more in the next class. There is a term called as Madelung constant, which is a useful term to know in the context of ionic solids, and then we will see there are certain rules which one needs to know to form the ionic solid structures, okay, which are called as Pauling's rules, and we will look at the structure of some of the common ionic solids. Okay. Thank you.